When nonmetals bond, they tend to form covalent bonds. Covalently bonded compounds can have either a simple molecular structure, like O2, Cl2 or N2, or a giant covalent lattice structure like diamond and graphite, where the strong covalent bonds extend throughout the lattice. This makes compounds with giant covalent lattice structures have high melting and boiling points, since it is these strong covalent bonds that need to be overcome when melting or boiling them, which requires a lot of energy in the form of temperature. Graphite is unusual as it forms hexagonal layers which consist of covalently bonded carbon atoms. There are weak induced dipole-dipole interactions between the layers, which allows the layers to slide over one another. This explains why graphite is soft and can be used as a lubricant. Only 3 of the 4 electrons in carbon are used for bonding in graphite. The other electron is delocalized, and this explains why graphite conducts electricity. Imagine if you took some sticky tape and removed just a single layer of hexagonally bonded carbon atoms from the graphite lattice. This is what some researchers did at Manchester University in 2004, and thereby discovered the world's first 2-dimensional crystal lattice, called graphene. Graphene has some amazing properties. It is around 300 times stronger than steel. It is extremely light, is flexible, transparent, and can conduct electricity better than copper. The first products made from graphene are starting to appear, and these include tennis rackets and cycling equipment. We are likely to see many more products using this remarkable material in the future. Simple molecular structures tend to have low melting and boiling points, since it is not the strong chemical bonds that need to be overcome when they are melted and boiled, but weak intermolecular forces. The strongest type of intermolecular force being the hydrogen bond, followed by the permanent dipole-dipole, with induced dipole-dipole interactions being the weakest intermolecular force, which occurs in non-polar molecules. When nonmetals and metals bond, they tend to form ionic bonds. Ionic compounds have a giant ionic lattice structure. For example, sodium chloride structure is made up of positively charged sodium ions, which are surrounded by negatively charged chloride ions in a continuous lattice. Ionic compounds have high melting points, since strong ionic bonds need to be overcome to melt them. In a solid state, ionic compounds do not conduct electricity, as the ions are locked in place with strong ionic bonds. However, in a molten state, or when dissolved in water, the ions become free to move and can carry the charge. Note, with ionic compounds, it is the mobile ions themselves that carry the charge, and not delocalized electrons. Metals form metallic bonds, which are formed from positive metal ions, and the outer electrons, which are delocalized. Metals form giant metallic lattices, which, like all giant structures, have high melting and boiling points, since the strong metallic bonds need to be overcome to melt them. Metals conduct electricity as the delocalized electrons are free to move and carry the charge.